Hey, hi, this is Vivek, and in this particular video, I'm going to share with you one of my personal favorite techniques in the whole realm of competitive programming, which is hashing, right? And this particular technique happens to be a generalized version where we know all about string hashing, which is permutation hashing essentially, but there is other versions of this too, which is very helpful at different places, right? And I feel not a lot of people know about SetHashes at least, and some people know about XOR hash, right? So how exactly do we go about doing hashing for CP is something we'll discuss, and we'll discuss some problems. In fact, I posted one particular problem in one of my last LinkedIn posts, and some of the suggestions were pretty good, but it was actually a problem of hashing itself, and we're going to discuss that problem today, right? And this is in fact the last video of this year, so I hope you guys enjoyed all the content that I've shared on this channel for this whole year. If you have enjoyed that, do subscribe to the channel. In the next year we will have more such techniques coming in, right? So let's get started with hashing. So the problem that I shared on my LinkedIn was this, that like the last video was dynamic connectivity, and the problem was this much, right? That you have n jars and there are q operations, and the operations essentially tells you to add a marble, like there is a marble of colors, and each marble of there are like different color marbles possible from 1 to n. The color can be in the range 1 to n, and you have to add a marble of color x in the range L to R, right? This is what you have to do in one type of operation. The other type of operation is you have to check if the two jars have the same marble. So let's say I happen to have four different marbles, right? And I put a yellow marble in this range, right? Then let's say a green marble in the range of this much. So a green marble gets inserted over here, right? Then a yellow marble in this range again. So that will insert another yellow marble over here, right? Then let's say I put up a green marble in this range. So that will insert just a green marble over here. And then maybe there is a query which tells us, Acha, find out if these two are same or not, right? And it turns out that they actually contain the same composition, right? So yes, then there might be a query that tell me if these two contains the same set of marbles or not. And it turns out that they don't really have the same set of marbles, right? So it's this particular type of queries that will be coming in, and we have to solve this in obviously like a good complexity. So when you have these range operations and stuff, obviously like something like O of n plus q into some log structure is what we expect over here for every query, right? Or some structure that we are building. So maybe log n or log square in max, right? So how do we solve this problem? So if you go ahead and try to solve it deterministically, it's fairly difficult. In fact, since many of you guys have not tried this, I will leave this problem as open challenge for anybody to solve this in a deterministic way in the comments, right? But since today's topic is hashing, I will like kind of go into different ways in which we use hashing, right? So this is a hashing problem. In fact, we have been like talking about comparing two sets. So what we will use is SetHash over here, right? And there are like three different types of hashes that we generally read about. Before that, there were like fairly good comments on this particular video, in this particular like post, which was one by Aruj, who happens to have another YouTube channel. If you guys don't know about him, do check out his channel, right? He also puts a lot of interesting content. So over here you have an idea of XOR updates on queries, but again, this is nothing but the XOR hash that we will talk about. This is the XOR hash that we'll talk about, right? And this is a fairly good problem, a nice idea of XOR hash over here, but XOR hash is not the one that we were using it. So using over here, and again in this particular thing, he suggested another idea, which is like polynomial hash, where we instead of like making it like polynomial, we just multiply. The problem with this multiplication kind of a function over here, right, is that like the multiplications can become same, right? 2 into 2 might become 4. There's a lot of chances of collision between over here. And the other problem over here that might pop up is uh, like what if something turns out to 0? Though it will not be the case over here, because we have the numbers in the range of, let's say, 1 to n, and we can set p such that it's never in the range of 0. But the chances of two different sets being same is very common in this one, right? This is a not a great not a great function, because if there is x1, x2, x3 and so on, right, mod some p, the chances of this being same for two different sets becomes pretty high very quickly, because with the number of terms and the product, there is a set of limitation. So in fact, there is like, this is also a good hashing function, but it turns out that for sets there is a better one, right? So that's what we will learn. Again, in fact, Navneet also suggested a good structure with bit mask plus suffix structure, which I think might be very difficult to implement. I'm not sure how this will work. Uh, One suggestion that he gave over here was square root decomposition, which is essentially what he's talking about is essentially square root decomposition on queries, right? Which is like delaying the queries by square root buffer. So you do the queries, like do square root of queries together and update that to a structure, and then maintain a buffer of last unupdated queue number of queries. And then when you query the similarity between two sets, you can go through the buffer and some previously built structure. But again, in that, the previously built structure will need the set. So in fact, if you don't know about square root decomposition, there are like 5 core ideas in square root decomposition that comes up. This is one of them, right? What he's talking about. 5 to 6 ideas that exists all together in square root decomposition. Maybe we'll cover that in some video in future, right? So this is there. And like, I think randomization problem solution is obviously like the best one. This one is another a really good solution that you can kind of use for this problem, that hey, go ahead and like store what bits kind of save you, like this is the set of bits that are on. And the only problem with this is like the colors might be same, so how do you update that in bit? You can try to use some trick that the second one goes to some other bit and stuff like that, but then it will not be often. So it might not be as simple as it seems, right? um, yeah, let's get into now learning, right? So these were some suggestions, but the correct set has still not been added to the comment. So I thought maybe it's worthwhile to make this video. And in fact, it's one of my most personal favorite techniques. Happen to have used this to solve so many problems in some competitions where it was not even the expected solution, like where you have to maintain a, like, let's say a grid, and you have to swap rows and columns and you have to check if the constituent set is same or not between two rows. So just maintain a set hash for that. And happen to have like solved way back a very hard problem, which gave me a lot of rating boost, right? Maybe I will find it and add it to the descriptions below, right? But let's look out these 3 hashing techniques today. So the first thing that we're talking about is permutation hash, which is fairly common if you have solved string algorithms. So in strings, we talk about hashing, right? Like let's say you have A, B, C. So what we do is we convert this into a number. Like what is hashing first of all? Hashing is just converting anything into a number so that you can compare if these two things are same, right? If the two original functions, so hashing is nothing but creating a function which gives you a y, and the way we work is like comparing two x's and computing them might be difficult, but we know that what's their y would be after hashing, and we try to compare the y1 and y2 and say that okay, if y1 and y2 are same, maybe x1 and x2 is also same, right? That's what we try to do, right, in hashing. So in string hashing, what we do is like we convert this to some sort of hashing, and in like the permutation is just like strings. We have some natural order of the 3 characters, right? And what we say in these cases is we do some sort of polynomial where we add these to the coefficients, right? We add a plus bx plus cx square. It can be other way around also, ax square plus bx plus c. So if you have heard about like rolling hashes, right? This is what we do in rolling hashes as well. Like we kind of build this structure, and there is one more benefit of this is that you can actually get a subportions hash, but that's not of concern for today. So if you have a permutation, the best way to kind of hash that is to actually put it into a polynomial structure, right? Why? Why do we do it in this way, that we put it in a polynomial? Like we take this string, we take a random x, right, and a random m, we compute this polynomial and take a mod, right? This is what we do. Why do we do that? So since a lot of people are not really that mathy person, I'm going to give you like an intuitive idea why this works, okay? So this ABCD over here that I've written, it's like the integer value of that might be used, or like in the range 1 to 26, right? You can use those numbers over here. So if you take any x more than, like, let's say 26, more than 27, right, greater than or equal to 27, or in general, like if you take x as a large enough, what you are writing over here is like writing the permutation in that base. So what we are saying is this is a x base number, right? And then converting it to a corresponding number, whatever that is, and then seeing it as if this is an x base number and seeing if that actually like is the same or not after converting it to decimal. So the way we handle permutation hashes is we assume whatever we have written is in x base, right? And then compare two numbers. So obviously, like once you convert to decimal, this number would be very large. So we computed mod m and then we compare. So obviously there is a probabilistic view to that, right? That okay, there can be collision even with a modulo and stuff like that. I will tell you a technique that you can use to like decrease down the probability by a big margin, big chunk, which is double hashing, right? But essentially what we see over here, the lens that we look it through is you are writing the permutation as if it's like digits of certain base number, and that base is what you choose as a randomization criteria. It should be bigger than like the digits that are there. Ideally, even since you are doing modulo, we are not getting anything ideal over here, so we can actually take it smaller too, but for it to work the best, you take it bigger than any of the numbers, and then you write it in a polynomial structure, take a modulo m, and you get the hash of that. So this is how you do it. So if somebody ever tells you like, okay, take an array 1 3 5 and hash it, right? What you do is simply take 1 plus 3, like let's say I'm taking the base as some a, and a plus 5a square. You can easily compute this number in a moduloed way with some modulo m, and you can return this number. This will be the hash of this permutation. Okay. Note that if you change the order 3 and 1, this will become 3 and this will become 1, and these are like two different polynomials, two different numbers in the base a. So they will not, ideally they should not lead to the same thing, right? That's what is the idea over here for permutation hash. So that's what we kind of assume in permutation hashes, and is the like the right way to think about permutations, right? But in this question that we were solving, we didn't had permutation, right? We had just sets, like it's just collection of marbles. It doesn't matter if the yellow came first or the green came first. This is something that is not useful over here, but again, this is something you can keep in mind. Okay, generally like you can use any like a over here and any m should be generally a prime modulo, and a can be anything bigger than the digits that you're using. Okay, let's come to the next interesting thing, which is SetHash, which ideally we should be using over here, right? And there are many ways to like hash a set, but the one that I personally loved when I learned for the first time, I think I learned it from Hassan in some particular problems it will, I don't remember that, to be very honest, but uh, the idea that is like used in set hashes is essentially to have, let's say, a collection a, b, or yeah, it can be numbers, it can be strings, anything, like it doesn't really matter, right? We can always convert it to some number. So let's assume a, b, c are three numbers. The way we convert this to set hashes is like this. So f of this set would be equal to some a plus some constant to the power another constant. Okay. Okay, so it's like you are adding bunch of things, right? You're adding bunch of things. This is not plus minus, right? You're adding bunch of things, and what we're doing is you're taking a power of h, right? And you're taking a k over here, and that is like what you generally use over here for like set hashing. Now this is one function that I've seen working very well in most problems. I've never got an issue with this one, so you can directly take this and use it. I'm not sure about other functions where you use multiplications, because I don't find multiplications to be that helpful in cases of like hashing, right? So this is like a fairly good one. Let me tell you the reason like why we are kind of getting into this. So what we are writing over here is essentially, like if you think about this, right? Let's think about just three terms over here. This is what is written. So generally the basis what we take k as like some number, some big number, like let's say 3. I just generally type it there itself, some random number when I'm typing this in code, right? Some 3 3 5 9 2 1 something, some random number, right? And h is like a pretty small number. It can go up to like something like 62 or some random number over here. Like I take some small number over here, some basic small number over here, but definitely more than 50. What are we doing over here when we write this h over here? Okay, what are we doing over here? So the idea is we are writing a polynomial, like for every term we are writing a polynomial. First of all, let's quickly see if the set hash of BAC will be the same or not. Obviously it will be same, because it's just as if like this term moved over here and this term moved over here, and there is a plus in between. And since plus is commutative, we can say that the hash for this and this would be same. That's very simple to see directly from over here. Now, why are we using this? The main idea behind it, how we can think about this particular thing is, this a plus k is like writing some k to the power h plus some like a power 1, some coefficient over here. I don't care about that, right? Some c coefficient, c1 coefficient, okay? K to the power h minus 1 plus kh, I should ideally write the coefficient 2, a2, kh minus 2, and so on, right? And you will get till a to the power h, right? H plus, right? Dot dot dot. And similarly, you will get bunch of like B terms over here as well. C1, B1, KH minus 1 plus C2, B2, KH minus 2, right? These are the, like, this is the second term. The first term is this. The second term, if you opened it with binomial, this is what you get, right? And now if you try to see, it's like writing a polynomial only. It's like writing a polynomial where the coefficients are the sum of powers of the actual elements of set. So it's like you're getting something like this. Let's go over here. So over here you are writing something like this. So you will get k to the power h plus, right, c1 times summation of a. So the individual elements a plus b plus c, right, this power 1, okay, and k to the power h minus 1, right, plus c2 a square plus b square plus c square times k to the power h minus 2, right, plus c3 a cube plus b cube plus c cube whole to the power k to the power h minus 3, right? That's what we use. So now when you see about this, like these are the coefficients, right? And when we say that two things are matching, two hashes are matching, why we can say that actual constituent set might be same? Because it's like saying that the sum is exactly the same, that for the two sets the sum is same, sum of squares of the element is same, sums of cube of their values is same, sum of 4 powers is also same, because they are like matching in their own corresponding coefficient, right? So that's why we generally say that this is a better hash, right? This is something like I have realized is much better hash than randomly using some power and a squares, just normal to few terms. So this is what you can use, right? And what we are saying is this is nothing but compressing powers, some powers into the coefficients of the polynomial, right? This is what it's doing. Obviously it's a modulo m and stuff, and we are doing in modulo m, so like it's all probabilistic, right? But naturally, if two things have all their powers same, right? This is a maths theorem though. If all this, if the two sets have all their powers same till actual number, like if you had gone till like whatever the sizes of set are, right? If all of those are same, then the set is actually same, right? That is true. But again, since we are doing modulo, we can actually like go with a smaller h right over here, and that should do the trick. You can always increase this, but it's not going to be any helpful because numbers are going to like kind of wrap around in the modulo and you're going to get something for that. So you can use any h over here. I've fairly used like something in between 100 to 200 should be good enough. And with using this big number, I sometimes use 37, some prime numbers, just to be sure about keeping it prime. That's it, right? But this is a fairly good idea that you can use for set hashes. So next time you see a set, you have to hash that up. Maybe just throw in these terms and you will get a hash for that, right? So that's how you get set hash, and that's the partial solution for the main problem that we were solving at the start. Now, after permutation and set hash, we have this XOR hash. So permutation and set makes sense, right? We have a permutation and we want to hash it up. We have a set and we want to hash it up. What exactly is XOR hash? Because that's very weird. So essentially, we want to kind of do a property of XOR, which is flipping. That means you have a 1. If you do an operation, it will come to 0. If you do that operation again, it will come to 1. So say the original problem happens to have this criteria that if you in a jar you put two yellow balls, they will like coincide together and kind of destroy both of them, something like this. So in that case, this problem would have been of a XOR hash, right? So the way we use XOR hash over here is use XOR obviously, but in a shifted way. Essentially, let's say you have a collection a comma b comma c over here, right? And what you do for this is you convert this into a hash by using a plus some shifted k, like you take a random number k, add it to all the things and take a XOR. That's what you do. So every time you add something, you add it to k and take a XOR with whatever was currently present, right? Plus k XOR c plus k. Now note very carefully, there is no modulo over here because like the natural property of XOR doesn't follow with modulo. So never use modulo with XORs, okay? Or be careful, because what we are trying to use is the bits property, but if you do a modulo, like that distorts that, right? So don't use a modulo for XOR hashes, right? And this k is what makes it important. Like this k is important. Don't use it just a XOR b XOR c. Reason being because it's very simple to create test cases where this will fail. Like 1 plus 1 XOR 2 is equal to 3. So let's say I give you a particular collection which has just 1 and 2 and a collection with 3, and I will know that your hashing function will coincide. Whereas if I add a random k, it's very difficult to predict whether the XOR would be same or not, right? obviously something will come back and something will like get to things. You can, if you want, you can use a mod inside this, like each element there is a conversion to some other element x using some function, right? And then that gets into the collection stuff, right? If you see in the previous stuff also, like in the set one, each element a got converted to a plus k to the power h, and then that got added in the collection. So since add is like commutative, we have a set hash, and then each element is being mapped into a way so that we get a logical idea that why these things would be similar if the hash is same, right? In this case also, we can convert this to some like random number, like every number has to be mapped to a fixed number every time. If that is the case, then we can use any function over here which maps it to some fixed number every time deterministically, and then we can use a XOR with that number in the collection that we are building. So that's the idea of XOR hash, and like that's used to kind of build numbers where if the same thing is added twice, you happen to have like 0 times, or like when there would be queries where things need to be there for odd number of times, you can use this, right? So find if the set contains all elements as even, right? Find out if this jar have even, like every color is present even number of times. In that case, you have to just check if the XOR hash of that thing is 0 or not, right? That's simple. So that's what we use for XOR hash, and it has its own applicability. So let's go back and let's see the main problem where we had to like kind of add. So there was a plus a color to the range LR, and we had to find if the two jars X and Y's are same or not, right? Add this color C to the range LR, color marble to LR jars, and this. So now when we have this plus, it's like adding this color marble to the set, right? So we obviously would build like a number which is C plus some K whole to the power H, right? And this is what gets added to the set hash. So it's like we have a range of jars, right? From 1 to let's say n, and these individually is like a set. Jar is a set, right? So we have to add this particular number to the sets in the range L to R, right? So it's like adding this number, let's call this as some number Z. So we are adding this Z in the range. So adding a number in the range, very simple problem. Segment tree can be used over here, right? Because the queries and pluses are intermingled, we have to use a segment tree, or else you could have done something like a partial sum too, right? So you have this particular idea over here, and then you have a query of x comma y, which is like, let's say you find out that, okay, this is x, and you find out, okay, its collection value is some number a, and like there is another like point y, set jar y, its collection number is b. And you can simply check if these numbers a and b are same or not. If they are same, most probably their collections are also same, right? That's what we have to do in this case. And it's like you have to add a number to the range, and we have to do point query. So it's like range addition point query, right? That's what we are kind of looking at over here, and which is fairly simple to do with a segment tree. Even you don't have to use lazy propagation. You can just, whatever range addition you are doing, just keep that in the node, and when you do point query, add the value in every node that you see internally. I'm not going to get into segment trees in this video because it's going to become difficult. You can read about this more. It's a very simple application, range addition point query. You can search for this and you will get some blog on Codeforces for sure, right? Or I think CP Algorithms blog also covers this on segment tree. So you can read about this if you want, but this is what we can use for this problem. The main idea is not really the segment tree part, is like how exactly do you compare two jars where things are getting added in range. And the main idea that you use is this set hash idea over here, right? Is that this number is what you have to add. So we have to choose a number k, and you have to choose a number h. Now there's this like a problem with hashing is that there is a chance of collision, which means two different sets, let's say a comma b and some c, might lead to the same hash, right? Same h if you use this function. So it might so be. The problem with this is you happen to see, let's say a comma b, which gets converted to a plus k whole to the power h plus b plus k whole to the power h, right? And let's say there is a c, which c plus k whole to the power h. Now you were using some modulo, right, on both the sides, and it turns out that after modulo these two numbers are same. These two numbers came out to be same, and that's very unlucky, but it can happen in modulo, right? In modulo domain. First of all, like which modulos to use, obviously I need not need to say this, but like you should use prime numbers, right? And what I've seen, if you're using a prime number, don't use the standard 10 to the power 9 plus 7, because people who are creating these problems are very senior and they know how to break these hashing functions using bunch of like techniques. I'm not going to get into that. Right, that could be in fact a video itself, like what is birthday paradox attacks and like these kind of hashing breaking functions, right? But don't use this. Instead, if you want to use some like prime numbers, I would generally suggest 10 to the power 9 plus 9 is a prime number. 10 to the power 9 plus 21 is also prime number. What I generally try to use is this 999, 999, 929, and then 999, 999, 937. These are also prime numbers, right? Just check it once before you use it, but I'm pretty sure this should be. So I generally use these two prime numbers, and that should be good enough. Like you can use any of these prime numbers over here. Don't try to use just this, right? And the second thing that you should use in such problems is double hashing, which is what is double hashing? So if these two things came out to be same, what if we found out another number, which is a plus k2? Let's call this k1 and h1, right? And m12, right? What if I use k2? Something very, very different, right? It's like one possibility of matching plus k2 whole to the power h2 and c plus k2 whole to the power h2 whole mod m1, right? m2. This is also mod m2. Now, by luck, these two came out to be the same thing. But there is a very low probability that these two will also come out to the same value, some h2, right? These two came out to the same value, but second time again with some new numbers randomly taken up, again the value getting to the same thing is very, very like less chance, right? There's a very less chance of that happening. So what we can say in this case is never use like just one hashing function like to compare. Like when you're like computing the hash for this, there is this one hash that you found, right? Use all again, keep like pairs, right? Don't use just one hash, keep pairs. So instead of comparing an integer, compare pairs. So now next time from this onwards, like if you have some collection, right, it will convert to, let's say, h1 and h2 using these two hashing functions. One is obviously you have k1, h1 and m1. Should have used some other name. So HA hash 1 hash 2, k1 h1 and m1 will give you the first hash, and k2 h2 and m2 will give you second hash. Generally you can also use these k1 h1 as same and just the modulo as different. That's also some people use as a strategy. I generally change everything, right? And you will get two hashes. Now two collections are only same if both the numbers are same, because if this is truly same, like if this is actually ABC and this is also ABC, right? No matter what you use over here, two different things, they will also come to the same number, right? But if like this is something else, let's say DEF, probability of getting both the numbers same with two different random hashing functions, which like the generator didn't know about, like the person who is setting the question doesn't know about, it's very difficult to create this, right? A person who is setting the problem, if he knows your K, H and M1, they can create test cases to beat you, right? This is the problem of hashing. So create random things, right? Be creative about this. Use random prime numbers that the generator cannot guess about, right? And this should be fairly good enough to like get through any like problem that needs hashing for that sense, right? So use double hashing to solve your problem of collisions with single hash. And generally for string purposes, we generally use double hashing itself, because if you're generating substrings, right, there is like 10 to power, like if there's a string is 10 to power 5 size, you generally have like 10 to power order of 10 to power 10 different strings. And like if these many different hashes are possible for different substrings, the collision chances is like divided by modulo, right? M1. So if modulo is 1, then it's very low chance. If you just multiply it with another modulo, like the chances of collision of two things is generally 1 by M1. The number of hashing, like whatever hashings you are using, the modulo M1, M2, you just multiply these things. If you use 3 hash, you can use 3 hash 2 if you want, right? Multiplied by the number of different possibilities. Right? This is what you use as a probability to get collision, right? This is fairly low if you use 2 modulos. So even in strings, generally prefer to use 2 different modulos, because I have seen problems where you would fail with using just one prime number. Okay, so use 2 different primes and technically use something that is not so common. 10 to the power 7 and 10 to the power 9 plus 7 and 10 to the power 9 plus 9 has become very common nowadays. So people guess that the people who are studying problems guess that these are the primes that you're using, right? So don't use them as often. Okay, so that's mostly the ideas of hashing that I wanted to kind of convey in this video, and I hope you enjoyed learning whatever we talked about today. if you enjoyed this particular thing, definitely give it a like, hit the like button that is there in the description. And to support creating more such content, definitely subscribe to the channel. You can always unsubscribe if you think that this is not going to be any productive for you later on, but liking and subscribing definitely helps me to make more such videos, right? Also, this is the end of this year, so happy new year to everyone who is watching this right now. Maybe if you're watching this later, so this is not me making sense, but again, I'm like always a well-wisher for you. Feel free to like reach out to me on LinkedIn if you want at any point in time. That's like I have like given the link in the description below. And like keep coding. We will have more such things coming in. You can always suggest me more such topics, individual topics, on the description in the comments below. And if you want to just say hi and help me like promote this video more, I mean just make the reach of this by YouTube Baba's algorithm to reach to more people, you can just throw in a comment and that should help me a lot. That's all from my side. See you all in the next video next year. Bye bye.